All right. Good morning, Tigers. This is Miss Gallant. This is going to be the first of a few video lessons I do for while I'm out on maternity leave. We're going to do today's lesson is lesson 33, applying quadratic equations. So you should have just had your quiz on solving quadratic equations, and now we're applying them. We're putting them in a real world context, and so that's where we're going with this. Okay, so the first thing I'm going to ask that you do is try task one, the spiral review. You should not need me to do a whole lot with this. Um, let's see. So I'm going to ask that you take some time to pause the video, try the spiral review. That would be task one, numbers one, two. Oh yeah, just numbers one and two. So the four tables and then the discrete and continuous data. So go ahead, pause the video, and try that. Okay, so here's what I have for the spiral review. Tables A and B are both linear. These two functions have a constant rate of change. So if I were to look at my x values on table A, these increase by 1, and the right side, the y values, decrease by 4. So for every 1x, my y decreases by 4. Okay, now B does not look like a constant rate of change if I just look at the y's, because from negative 6 to 4, I'm increasing by 10, then I'm increasing by 5 from 4 to 9, plus 10 plus 5. Well, that doesn't look constant, but if I look at my x's as well, from negative 2 to negative 6, I decrease by 4. From negative 6 to negative 8, I decrease by 2. Decrease by 4, decrease by 2. Remember, your constant rate of change is how much you change for one x to the next. So what I could do is I could find the slope between each point. So I could take my y's and subtract, my x's and subtract, and divide. So 10 divided by negative 4 would be negative 5 over 2. 5 divided by negative 2 would be negative 5 over 2. So the slope is the same. They're changing by the same amount. We just skipped values, and that's okay. Okay, in C and in D, both my x values increase by 1 from each row, or from one to the next. My y's, on the other hand, I go from 0 to 2, from 2 to 8 is 6, from 8 to 10 is, from 8 to 18 is 10. The left side's increasing by the same thing, but the right side is not. So this does not have a constant rate of change. Same here. Now this one's a little tricky because if I'm looking, I'm adding 0.5, then adding 1, then adding 2, then adding 4. I know somebody is going to come in and correct me though and say, hey, you're doubling, you're multiplying by 2, which is true, but that's not a constant rate of change. That's a common ratio. So it's something different. In order for it to be linear, it has to add by the same amount, not multiply. All right. Excuse me. Sorry, just out of breath a little bit from having this baby, or from still being pregnant. So bear with me on that. All right. And then number 2, ask you to look at the examples of discrete and continuous and come up with a definition for each. So if you look, all the discrete data is individual data points. It's just dots. So we're going to call them individual data points. Discrete is not connected. Continuous, a lot of people are going to say, oh, continuous, it has an arrow, goes on forever. Doesn't necessarily have to go on forever. It's just data that's not broken up. It's connected by a line or a curve. Doesn't have to go on forever. In fact, neither of these have arrows on them, so they stop. They have endpoints. But from the starting point to the end point, it is continuous. There's no breaks. All right. All right, so let's turn around and look at task 2. This is one of my favorite lessons, favorite little application problems. So, all right, so we have, let me scoot this down. All right, Daniel Bowe absolutely loves model rockets, mostly because he likes to blow things up. But this time, Daniel Bowe wants to collect some data on his model rockets to see how high they reach and to try to improve the height reached with each rocket, and then he can blow them up. All right, so Daniel Bowe's rocket is called the Kerbal. Once the engine is ignited, it can burn for 3 to 5 seconds. The rocket's going to accelerate upward. And this rocket has a parachute that will open as it begins to fall back down. So Daniel attaches a device to the rocket so it'll collect the data the moment the engine shuts off. So our data starts the second the engine shuts off. Unfortunately, the parachute failed to open, so when the Kerbal begins to descend, it's in free fall. Okay, so this is the data we have. So he's launched his rocket, the engine shuts off, and it starts collecting data on the height as it falls. And I want you to think about it for just a second. It's when you've got your rocket and it's going, after that engine shuts off, you've got some momentum, so it's still going to go up a little and then fall down. So it's going to go up, it's going to shut off, it's going to go up just a little bit more, and then boom. Okay, so we're going to graph the equation to answer, or graph the data to answer the questions below. So, number 3, can the height of the Kerbal be modeled with a linear function? So let's think about it. Again, it's accelerating, it's going up, the engine shuts off, it goes up a little more, it's going to fall down. That's not linear. Our height is going up and then down. So, no, this is not a linear function. So we have our height increases, then decreases. So it increases and then decreases. Also, if I look at this data, it's not a constant rate of change. I would say I don't really feel like calculating it, but the jump from 512 to 560 is much greater than the jump from 560 to 576. And then we change directions completely to decrease. So it's not going to be linear. There's no constant rate of change. Okay. All right, then it asks us to graph the data for the height of the Kerbal as a function of time on the grid. So it is just asking for the data. So we're just going to graph the points. All right, so we're going to start with 0, 5, 12, which will be about here. It doesn't have to be perfect, but I should be able to tell the difference between 512 and 560. But like, I'm not going to go in with a ruler and measure, like, is it exactly 560 or is it 554 or something? All right, 1 560, 2 576, 3 560, 4 512. Let's see, 5 is 432, and 6 is about 320. It's about here. So we're just going to graph the points here. Now, number 4 asks, should the data be discrete or continuous, and why? Well, right now, I'm going to leave it discrete because it did just ask for the data. It didn't ask for the function. However, if you're thinking about this rocket, it's not going to, at 0 seconds, be here, then poof, disappear, and pop back up at this point, and then poof, disappear, and then pop back up at this point. So the data should be connected, but we're going to leave it discrete because that's what it asked. So data should be continuous because it's not popping out, it's not disappearing and reappearing. It's a continuous flight. The height is constantly changing. But we're going to leave discrete for now and connect later. We are going to connect it. We're just going to connect it in a little bit once we have an actual function. Okay, task 3. Using data and estimation. So we've got 3 questions. How high was the Kerbal when the engine burned out? How long did it take the rocket to reach its maximum height after the engine cut out? And once the rocket begins to descend, it's in free fall. Estimate how long the Kerbal was in free fall before it reached the ground. So I'm going to ask that you answer these 3 questions. Now remember, the data didn't start collecting until the engine burned out. So the engine burned out at 0 seconds. So that's where we're starting our data from. So how high was the Kerbal when the engine burned out? Kind of give me the answer there. When did it hit its maximum? You can use the graph or the table. And 7, how long was it in free fall? So not what time did it hit the ground, but how long was it in free fall? And it's in free fall once it starts to fall down. So I'll give you a few minutes to get some answers for me. Okay, so we're going to check our work real quick. So task 3, how high was the Kerbal when the engine burned out? So the engine burned out at 0 seconds. So if I check my table at 0 seconds, we were 512 feet in the air. You can also check your graph. That would be your y-intercept. There we go. All right. Question 2, how long did it take after the engine cut out for the rocket to reach its maximum height? Well, that maximum height should be at the vertex, which is at 2 seconds. Going back to my table, at 2 seconds, we hit 576. That is the largest number in this column. So at about 2 seconds, I would say we hit our maximum height of 576 feet. And then number 7, how long was the Kerbal in free fall? So let's look at our graph real quick. It hits its maximum height here at 2 seconds. And then it's going to fall until it hits the ground. We don't have any more data past this point, but if I were to connect it and kind of follow that pattern, I would say it's going to hit the ground at 8 seconds. Now, it started falling after 2 seconds. So from 2 to 8 seconds, that's a total of 6 seconds in free fall. So we're going to say it hits the ground at roughly 8 seconds. We don't know for sure. We're going to find that out in a minute. But if it hits the ground at 8 seconds, then it was in free fall for about 6 seconds. Okay. Task 4, quadratic regression. So, what regression is it's a way for me to use a table and type some data into Desmos. And when we do that, we can get an equation out. So I'm going to try to keep the instructions and Desmos up here together. I probably won't be able to get both of them up all the time, but we'll try to go back and forth. So at this point, you need to pause the video and open up Desmos, and then you can restart the video and listen to me while you're working through Desmos. So go ahead, pause, get Desmos set up, and then when you're ready, start back up. Okay. So we have, all right, so you should have Desmos up. Once you've opened Desmos, you're going to click this little plus sign at the top. So I'm going to actually get rid of this. You're going to hit this little plus sign right here. Okay. And all right, we're going to insert a table. All right, so in this table, we are going to type our data from the problem. So we're going to flip back. We're going to type in this data into this table. Okay, so the time in seconds will be your x1, your height in feet will be your y1. All right, so we're going to type in 0, 1, and after a couple of clicks, you can just start hitting enter and it'll follow that pattern for you on the X's. Y's are always a little different. It's not going to do the same thing, so we'll have to actually manually type these in. Okay, 512, 560, 576, 560, 512, 432, and 320. Okay, so notice you do not see the points on my graph. Okay, if you look at your instructions, it does say, if you cannot see it, click on the wrench and adjust your Y and X axes till you can. So we're going to click on this wrench up here. And then let's look at our X values. We go from 0 to 6. If I look at my graph on that we graphed in task 2, our time went from 1 to 10. So let's go, just to give us some breathing room, let's change that to -1. Leave our X at 10. Our Y's, our rocket goes from 0. Let's leave this at -10 just so I have some breathing room. And we go up to 700. All right. And now you can see I have all my data graphed. Okay. All right, so we have our data graphed. Okay, number 10, does your graph you drew by hand match the graph on Desmos? Double check and make any necessary corrections. So look at my little graph here. Obviously, it's going to be a little different because of the shape of the graph, but my maximum doesn't quite get to 600. It comes down some. So they both look to be quadratic, so we should be good. All right. Number 11, underneath your table, type in this formula. Y1 regressed against ax1 squared plus bx1 plus c. A curve should appear through all your points when you type this. All right, so go in here. When you type, you can type y and then just type the number 1 and it automatically drops it for you. 1 second.
Good morning, teachers. Pardon this quick interruption. I need any student that is running cross-country next school year to go to Mr. Matthews' room at this time for a brief meeting. That is all students that are running cross-country next year. Please go to Mr. Matthews' room, A104, for a brief meeting. Thank you.
Okay. So we're going to type in Y1. This little squiggle, you can find it in the top left corner of your keyboard. Or, let's see, if you need to, down here, you can do show keypad, this ABC, and down here is a little squiggle. So you can always use the keypad. I normally just use the keyboard though. Okay, move this back down. All right, so we have Y1 regressed against, we're going to type in A, X, type in the number 1, Shift 6 for an exponent and squared. So we have AX1 squared plus BX1 plus C. So if you look, this is standard form of a quadratic equation. We just added the 1's in. The 1's come from our table. We have X1 and Y1. If I had multiple columns like a Y2, a Y3, so on and so forth, which you could do so that you don't have to type in 3 tables, you can just type in one. That you would have to change your X and Y's to match your list. So that's just a quick little shortcut. All right, so if you notice down here, right down here, we have an A, a B, and a C. We have an A, a B, and a C in our formula. So this is our A value, our B value, and our C value, which is pretty cool. So let's go back to our worksheet. We should have a curve appear through all of our points. We have these parameters right down here, and we're going to fill in our equation. We're using h of t because we're using t for time, and h of t is the height of the rocket. So we're going to start with our a value is negative 16. So we're going to have negative 16 t squared. Okay, then we have plus bx, so plus 64t. And then plus c, our c is 512. Okay, and that is our function. You could find this by hand. It would be a pain in the butt though. So that's the beauty of Desmos, is you can do regression in a calculator. All right. So task 5, using the function to answer questions. Okay. Number 12, sketch the graph you just created on the grid for question 4. So we're going to go back to 4. We're going to sketch what we just did on Desmos. So what I want to look at, we do hit the ground at 8 seconds. So we do have that point. So let's make sure we have that point down here. And then we're just going to connect and hit that point. Okay. All right. Then going back to task 5. All right. Identify a reasonable domain and range for this problem. So let's think about this. It's a rocket. Domain is our x. And we're measuring time here. So when we think about our rocket, we're not going to measure past the time the engine burned out. And we're not going to measure past when it hits the ground. So our time, our rocket is in the air from 0 to 8 seconds. All right, our range is the height of the rocket. Okay? It's the height of our rocket. So the lowest point, the lowest height our rocket should hit is the ground, which would be 0 feet off the ground. And then its maximum, the highest height it reached, was 576 feet. And something I kind of forgot about, we're not using x and y in this. We're using t and h of t. So what we could do is use t and h of t in our domain and range. That's something I kind of forget about every once in a while. It doesn't change the domain and range, but it does force you to use the same variables. So it doesn't change the answer, but it does change the variable. Okay. So for 14, use the function you found in question 12 to verify the height of the Kerbal when the engine burned out. So our function we just wrote was negative 16 t squared plus 64t plus 512. Now, we said the engine burned out at 0 seconds. That's when we started collecting data. So we're going to plug 0 in for t. And you can plug this whole thing in the calculator, or you can just use some common sense. Negative 16 times 0 is 0. 64 times 0 is 0. 0 plus 0 plus 512 is 512 feet, which is what we had in the table, which is also what we said on one of the previous questions, on question 5. We said 512 feet. So we should be good here. All right, 15. All right, 15. We're going to use the graph to approximate the time interval in which the Kerbal was in free fall and then explain how we determined your answer. So if we go back to the graph, we hit our maximum here. We hit the ground here. So we were in free fall from 2 seconds to 8 seconds. So we're going to say the Kerbal was in free fall from 2 to 8 seconds. That's 6 seconds total. All right, and I'm going to depend on y'all to come up with a good explanation for how we came up with that. Okay, so I have a class coming in, trying to film very quickly. We're going to look at task 6. I'm actually going to see if you can answer questions 16 through 20 on your own. So this is solving a quadratic equation. We're finding the x-intercepts. We are going to get to a point, though, when we want to find out about when the rocket reached different heights. So I'm going to ask that you try 16 through 20. Pause your video. Once you've tried all of those questions, you can go ahead and resume the video. Okay, so everybody should have tried 16 through 20 on task 6. So if we look, number 16, what does h of t represent in this context? So h of t in our problem should be the height of the Kerbal rocket. T is time and h of t is height. Number 17, what must h of t equal if I want to know at what times the Kerbal is on the ground? So what if the Kerbal's on the ground, if the rocket's on the ground, what is its height? Well, it should be 0 feet off the ground if it's on the ground. All right, 18, rewrite the function h of t so that it is equal to 0, then solve by factoring. So I replaced h of t with 0. In this step, I factored out the greatest common factor, which is negative 16. And then I need two numbers that multiply to give me negative 32, but when I add them, I get negative 4. And that would be negative 8 and 4. So I have negative 16 times t minus 8 times t plus 4. If I divide both sides by negative 16, this cancels. 0 divided by 16 is still 0. I'm left with t minus 8 and t plus 4. And I'm going to set those both equal to 0 so I can solve. Add 8 to each side, I get t equals 8. Subtract 4 from each side, I get t equals negative 4. So what this is saying is that the two times when the Kerbal is on the ground is at 8 seconds after the burnout and at negative 4 seconds after the burnout. Which brings us to question 19. When you solve this equation, you have two solutions. However, only one of them makes sense. Which one is it? We can't do anything with negative time. Negative time does not make sense. Positive time does. So this is 8 seconds after the burnout. This would be maybe, I guess, 4 seconds before the burnout. But, we can't say -4 seconds. It just doesn't make sense. Also, when it's on the ground, we don't know exactly when that engine burned out or anything. So we're not 100% sure. So this one really just does not make sense because it's a negative. And we don't mess around with negative time. We are not Doc Brown. We're not Doctor Who. We can't do that. All right. And then number 20, write your solution as an ordered pair. So 8, 0. At 8 seconds, the rocket's height was 0 feet. All right, number 21 says go back to your graph, draw a horizontal line to indicate a height of 544 feet above the earth. And we're going to figure out when the Kerbal was at 544 feet. So if we go back to the graph, this line would be 550. So let's do it in blue so it shows up. So 544 should be just below that. And if I look, I didn't connect that very well. But if I look, we have it maybe half a second and let's see. Oh, that should be, I didn't connect that very well. And maybe 3.5 seconds. So right about here. If this were connected better, right about there. So about half a second and 3.5 seconds, we're at 544 feet. So we're going to do approximately 0.5 and 3.5 seconds. And you may have something different depending on how you connected your graph. Now mine, I'm looking, I'm like, oh, I didn't connect that very well at all. But yeah, roughly 0.5 at 0.5 and at 3.5 seconds. So we want to figure out the exact times. So first thing I'm going to do is the last one we solved, we set our height equal to 0. And that was when we found it on the ground. But I want to find out when it's at 544. So I'm going to rewrite my equation, but I'm going to make h of t 544 instead of 0. So negative 16t squared plus 64t plus 512. Now remember, when we solve equations, when we solve a quadratic equation, we want this to equal 0. So what I'm going to do is I'm going to go ahead and subtract 544. Okay? And then that's going to give me 0 equals negative 16t squared plus 64t minus 32. So this is a different equation than what we had in question 18 because the c value is different. So it's going to give us a different answer, but we still have it set equal to 0, so now we can do any one of our solving methods. All right, so 23 asks, what method would you use to solve this equation and why? I can't answer that for you. Some of you are going to try to factor, which is, I wouldn't go that route because I don't think it's going to be factorable. Some of you are going to graph it, which I normally would be okay with, but you're not going to be able to get an exact answer. So let's not graph it. So that leaves you with square roots. It has a b value, so I wouldn't square root it. That kind of leaves you with the option to either complete the square or do quadratic formula. I'm comfortable with either one. It does not matter to me. Either one of them will get you the same answer. So you answer 23 and with what method you would use. Personally, like the two methods I would suggest would be either completing the square or quadratic formula. All right. So 24 and 25. 24, I want you to solve that equation we just wrote. And then I want you to answer 25. Now 24, let's change these numbers real quick. because it says the equation you wrote in 18. This should be the equation you wrote for number 22. And how does it compare to your answer from number 21? So you're going to solve it. You're going to check to see that your answer was close to what you got in 21 when you graphed it. And then it does ask you to round to the nearest thousandth. So remember, nearest thousandth would be, nearest thousandth would be 3 places behind the decimal. So that would look like point as tens, hundreds, thousandths. So there should be 3 numbers behind the decimal. So I'm going to ask that you do 24 and 25. Pause the video, try it yourself, and then check your answers with mine. Okay, so looking at our answers for 24 and 25. So 24, what I did, we're just solving this equation. I completed the square. You could have done quadratic formula and gotten the same thing. When I complete the square, what I did was I divided everything by negative 16, and that worked out. It was the greatest common factor again. I'm left with t squared minus 4t plus 2. And I did try, you cannot factor this. So after that, I subtracted 2 from each side and put in my boxes to complete the square. So here, half of negative 4 is negative 2. Negative 2 squared is positive 4, so I add positive 4 to each side, which gives me 2 equals t minus 2 squared. Take the square root of each side. I'm left with plus or minus square root 2. Add this 2 to each side. I'm left with 2 plus or minus square root 2. 2 plus the square root of 2 is 3.414. 2 minus the square root of 2 is 0.586. So my 2 times are 0.586 and 3.414, which if we look, when we made our predictions, we said at about half a second, that's reasonable. And at about 3.5 seconds, which is reasonable to this too. All right, 25. Why do you think you were asked to round to the thousandth place as opposed to giving a whole number answer? We have data for the whole number seconds. We already have that data. We don't have data for anything in between. So at 0 seconds and at 1 second, I have a height for this rocket. At 0 seconds, I have a height that's lower than 544. At 1 second, I have a height that's larger than 544. 544 is about halfway in between, and that's our exact answer. If we rounded it to a whole number, then we're covering up some data already. The change in height is continuous, and we want data that reflects that. It's every millisecond the height is changing, so we want to make sure that even at 1,000th of a second, we know that the height is different between 0.586 and 0.6. It's going to be different between those. All right. So, task 7, question number 26. I'm going to ask that you try this section on your own. I'm not going to post answers in the video. You can check it with the key later, but I want you to try 26 on your own, okay? Your next quiz, quiz 7, is going to have questions like this. So make sure you know how to interpret it. The LEAP test is full of questions like this too. So make sure you can interpret the question, make sure you know what it's asking, and and check your answers with the key later. Good luck. Thank you for paying attention today, and hope you have a good day.